Imagine looking up at the night sky, knowing that right at this moment, a massive piece of human engineering is racing toward the lunar surface at thousands of kilometers per hour. Specifically, this was a 4-ton upper stage of a SpaceX Falcon 9 rocket, left drifting through the void long after its primary mission was complete. Usually, a rocket launch is a highly controlled sequence. The first stage returns to Earth for reuse, while the upper stage drops off its payload and then either steers back down to burn up safely in our atmosphere or gets pushed into a harmless disposal orbit. But in this case, the upper stage had finished delivering its payload on a lunar trajectory. Instead of falling back home, it stayed out there, becoming a high-speed, rogue projectile trapped in the deep. This model traces what happens next. The rocket's trajectory got caught in a chaotic gravitational tug-of-war. Pulled by the Earth on one side and the Moon on the other, it began tracing an unpredictable, erratic path. Researchers carefully monitored this flight path for years. Eventually, their calculations zeroed in on an unavoidable conclusion. The 4-ton cylinder was on a direct collision course with the lunar surface. When news of the impending crash broke, it sparked immediate anxiety. People wondered if an explosion of that magnitude could actually shift the Moon's trajectory and put Earth at risk. The impending crash offered a rare, unscripted test of our orbital physics models, a chance to measure the raw power of a high-speed impact on a planetary scale. Out on the far side of the Moon, near the Einstein crater, the rocket slammed into the dirt. Because the Moon lacks an atmosphere to cause drag and slow things down, the cylinder struck at its maximum velocity of roughly 8,700 kilometers per hour. In a fraction of a second, that immense kinetic energy instantly vaporized the metal and excavated a fresh crater measuring anywhere from 10 to 40 meters across. On Earth, an impact like this would eventually weather away, but the Moon has no wind, no rain, and no flowing water to erase the damage. For scientists, this sterile excavation is incredibly useful. Lunar orbiters are now scanning the site, measuring how the deep soil behaves to improve our computer models for predicting asteroid strikes. What started as a piece of discarded space junk has become a permanent scientific experiment, carved into the rock for millions of years. So, what about that fear that hitting the Moon at 8,700 kilometers per hour could somehow knock it off course? On one side, the incoming rocket weighed a few thousand kilograms. On the other, the Moon weighs over 73 sextillion kilograms. The rocket's kinetic energy is mathematically invisible against the Moon's staggering inertia. The impact simply isn't large enough to move the needle. Giant celestial bodies are entirely immune to our current space debris. But human engineering is a completely different story. If we zoom away from the invincible lunar surface and travel back to Earth, the environment changes entirely. We rely on a fragile, densely packed network of satellites operating just above our atmosphere. Sharing that narrow airspace are thousands of dead satellites, spent rocket stages, and metal fragments, all racing around the globe at those same terrifying, uninhibited velocities. If we apply that math equation here, the math gets very dangerous. Unlike a moon, a communication satellite doesn't have sextillions of kilograms of rock to absorb an impact. The true danger of rogue debris is the catastrophic high-speed shattering of the very technology that runs our modern world. And a single collision in orbit doesn't just leave a neat crater. It instantly creates thousands of new, lethal pieces of shrapnel that fan out to strike even more satellites. That threat has triggered a massive technological race. Space agencies and private companies are actively designing systems with magnetic tethers and robotic arms to safely capture and remove this debris before it multiplies. Right now, hidden in the shadows of the Moon's far side, there is a brand new scar. It serves as a permanent, silent monument to how rapidly our reach into the solar system has expanded. As we launch deeper into the cosmos, mastering the cleanup of the orbital pathways we leave behind will be just as vital as the rockets that carry us there.